All right, in this problem, we are working with a situation where we have a car is stopped at a traffic light, travels along a straight road, and they give us a position function where in that function, the B and C are constants, and those are provided for us here as well. Okay, so they tell us first to calculate the average velocity of the car over a specific time interval. So if we have a position function, we can just use our basic definition of average velocity. So V average, and I'm just going to specify in the x direction, is going to just equal my change in position over change in time. We are able to calculate that change in position. So here we want to do that across the time interval. So we're going to do x at time t equals 10 minus x at time t equals 0, right? So my change in position is my final position minus my initial position, and I can calculate those by plugging in the corresponding times to my position function, and then we're going to divide by my delta t, and so in that case, this is just 10 minus my 0. So we started at 0 and we're ending at 10. So for this, all we're going to do then is plug in for x at t equals 10. I'm going to plug in t equals 10 to this piece right here. For t equals 0, we're going to plug that in there as well, and then divide by 10. And so if we do that math, we are going to end up with 12 meters per second. It is asking for a velocity, so I'm going to go ahead and indicate a direction there. I didn't end up with a negative direction, so I'm just going to be kind of over articulating that direction piece by putting that positive sign out front. So average velocity, just change in position over our change in time. For B, we're asked for instantaneous velocity. So for instantaneous velocity, we want to do the derivative. So we have, again, that position function. But my V, this time I'm going to write my V like this. I'm just taking out that average piece. I'm still using that X subscript to indicate that we're focused on just that X direction. So V sub X, and we're going to develop this function. So this will be as a position of time. So I'm going to say V sub X, sorry, I can't write this, V sub X as a function of time is going to be equal to that derivative of X as a function of time, dt. So we're going to do dx dt. So we can go ahead and plug in. So I'm going to do ddt of my position function, which was bt squared minus ct cubed. Okay, so if I go ahead and do that derivative, we end up with this, which I will call our general expression for our velocity. So this is going to be 2bt minus 3c t squared. Okay, so I'm going to highlight this. So this is our general expression for velocity, just where we would call this one up here. This will be our general expression for position, right? And this problem, looking ahead, doesn't ask us anything about acceleration. But if I wanted acceleration, I would do the same thing. I could come up with a general expression for acceleration that is based on the derivative of that velocity function. Okay, so we calculated the general velocity function. They asked us in B to calculate the velocity at these certain points. So we have 3 points we're interested in, t equals 0, 5, and 10. So we're literally just going to plug into this function that we just calculated. So we have V sub x at t equals 0, V sub x at t equals 5 seconds, and then V sub x at t equals 10 seconds. So I'm just going to plug that 0, 5, and 10 into that expression we just calculated. So I'm going to just throw those numbers up here. This is going to be 15 meters per second. And then that last one is going to be 12 meters per second. Okay, so once I have that general expression, I can find my instantaneous velocity at any time. All right, let's look at C. C says, how long after starting from rest is the car at rest again? So big idea here is we want to just remember that if I'm at rest, that means that my velocity is equal to 0. So if I'm looking for times where I'm at rest, I want to set that velocity function equal to 0, right? So I want to set that equal to 0, and then we will solve for the times where that is true. So I'm going to take just this piece up here, our general expression. I'm going to rewrite that down here. So we've got our 2, make sure I can see it. So we have 2bt minus 3ct squared. that's going to equal 0. And now I'm solving for t, right? In the previous two parts of this problem, we were plugging in t and solving for velocity. Here we want to know where, at what times is our velocity equal to 0. So we know our v, here we're solving for t. So I'm going to factor out a t. So this is 2b minus 3ct not squared. So I factored out my t. So t times 2b minus 3ct equals 0. So I have two solutions for t that are valid here. So this one, t equals 0, gives me v equals 0. And then when this piece in here is equal to 0, so 2b minus 3ct, when this is equal to 0, I can find that t as well. So here t is, we'll move that 2b to the other side, divide by my 3c. So the time, the other time where my v is going to be equal to 0 is 2b over 3c. And remember that the b and c, those were constants. So I can hop back up here. I'm going to go ahead and plug in b and c there. So if I plug those in, we end up with our second time where velocity is 0 is 13.3 seconds. All right, so for this problem, kind of big ideas for this one, we just want to recognize that if I have that position function, anytime I have a position function, I can calculate a velocity function, a general function for velocity from that by taking the derivative. Again, we didn't do it here, but I could also calculate the acceleration function. I can do an average velocity. So in this problem, we're focusing on that difference between an average velocity, which is just that change in position over change in time, and then that instantaneous velocity, which is going to tell me the velocity at a very specific point in time.